Hello everyone, I'm Rahul, and in this tutorial I'm going to explain you how to draw a layout using Magic VLSI layout design tool. So it's an open source, so you can download it from the website. Okay, so I'll start by invoking the software. I'll type Magic. These two windows will get popped up. Okay, so for this layout design, I'll be using the references from the slides of Professor A. Mason, who is from Michigan State University. So he has given brief about this layout design. So first we use layout editor and we'll draw our layout following the design rules which are given. So it is recommended to check DRCs after each drawing, and once there is no DRC, we try to extract parameter which comes under packs analysis or parameter extractions. So after that we do LVS, layout versus schematic. So in this we can interpret the difference between the response of layout and the schematic. So let's start with the tool. So these two window is already here. So like if I press the G, so the grid will come, and if I press Z, so it will zoom in, and if I press Ctrl Z, so it will zoom out. So next I'm gonna click on the option and we'll select the toolbar. So you will get these various structures here, and once you take your pointer on any structure, it will give you the information at the top right corner. Like now P well is selected, next is N well, cap well, and these metal 1, metal 2, like that. And these below are contact, various contacts are there. Okay, so as I already told you, this is an open source, so all the facilities are not available here. So like you can see, only 3 metals are there, but in general there are many metal layers. So I'll explain you what are these all metal layers and how we use them. So before that, our aim is to design the layout and extract its net list. So I'll explain you everything. What are these metal layers and what is the need of different metal layers. So we'll go step by steps. So first I would like to tell you, if you go to the option and click on Tech Manager, so some technology files are there provided by MOSes. So by default this SCMOS is selected. In this, micron by lambda is equal to 1. That means 1 lambda is equal to 1 micron. So we keep this one only. So these one box is lambda. So now the question is how to draw the pattern, various pattern. So to understand this, we'll take example of inverter. We'll design the layout of an inverter. So let's see how it looks like. Suppose this is one PMOS, okay, connected to VDD, and the lower one is NMOS, and its source terminal, we are making it ground. So we'll provide input from here, and output is taken from the common drain. So we'll get the output from here. So this is the basic structure of inverter. So we'll try to draw the layout for this. So like before drawing layout, I also would like to explain you the click pattern of the mouse which we will use for designing the layout. So it's better to use a mouse instead of trackpad because it requires three kind of click to draw these layouts: left click, right click, and the center click, which is generally available in the mouse. So by this left click, I can change the position of this square, and by right click, I can make the square. I can make the design. Okay, so I can make it as small as the pointer or as big as. Okay, fine. And what is the role of center click? So suppose I have drawn this structure here, and I want to and I want to make it as a poly. So I'll go to the poly and will press the center. So this will become the polysilicon. Okay. So I'll press the U for undo. All right. So like here still DRC is 0. When we draw poly, there were no DRC. So these rules can be found here itself. Just try to draw something, and if it is wrong, so DRC itself will activate it. It will show 1, 2, or 3, something like this. So suppose again I am drawing the poly. So I have made I'm using a single cell. Now if I clicked here, so it is showing those white dots. So and here it's DRC2, so there is some error. So what are these errors? We can find out from here by writing DRC space find. So it is written polysilicon width must be at least 2. So this is the Moises rule, but for us we have drawn 1 lambda. So now I can extend it. Now it's fine, there is no DRC. So like by drawing various structure here, we'll be able to know the DRCs or its rule. Suppose I want to draw a metal in next case. So this has been selected. So it's metal 1. I'll press the center click. Okay, so again it is showing these error. DRC becomes 2 now. So I think it must be like the minimum metal layer should be at least 3 lambda, because 2 blocks are covered with white dots. So let's see DRC find. Yeah, just the same. First level metal width must be at least 3. So we can extend this. So now DRC is 0. Okay, so this way you can find out. So I'll again press U to undo the thing, or yeah, I can delete also. So for deletion, what will I do? I'll just select it. I'll just make it a square. So these square I'm making by pressing right click, and I will center click here. So it will get removed. And another way to remove it, just select it and press Ctrl D. Okay, so rules related to this tool and their DRC can be found on internet easily. So since this magic VLSI tool is developed by Berkeley, so if you type magic Berkeley, so you will get one web page. There you can get all the information that how to move, how to delete, redo, undo, everything is there. So there are few tutorials, you can follow those for different type of layout design. And you must have observed here when I checked for DRC, so it is written Moses rule 3, rule number 3.1, rule number 7.0. So what are these rules? So these rules can also be found in this website. So like rule number 1.1, what is that? The well width should be 10 lambda, like that. Poly space, rule number 3.2. So all rules are written here, you can directly see the rules. Or you can also, you will also get to know once you'll start designing the layout, once the DRC will come. Okay, so in the description below I'll give a link which will consist the very much required shortcuts and the rules, so you can go through before drawing this. Okay, fine. Let me quickly start the layout of inverter. So this one you have seen, it's an inverter which is the combination of PMOS and NMOS, and these are connected in one specific manner. So before starting this layout, I want you to see the 3D diagram of inverter. So it looks something like this. So this yellow color is P substrate. So for this entire surface is P substrate. So for making NMOS, you need nothing but 2 N plus diffusion, because it's already P substrate is there. But for the PMOS, as you need P plus diffusion, so before that you are required to create the N well. So here you will create N well, and in N well you will create the P plus diffusion, and these are the gates which is made up from poly. Okay, so we'll start with the PMOS. So I'll make a big structure for, okay, or I should make a bigger one. So this layout which I'm going to draw may not be optimized at the beginning, but after that we can optimize it. So this one should be the N well. So I'll select the N well from here. Where is N well? P well, N well. Yeah, this is the N well. So I'll press the center click. So it becomes N well. Okay. So after this N well, I should have P plus diffusion. So for P plus diffusion, I will select it from here. So, but before that, I'll make a drawing for that. But keep your eye on this. DRC is to 0. That's good news. Okay. So here, now I will select the P plus diffusion, P diffusion. So P diffusion, where is the N diffusion, P diffusion. Okay, I will select this. So it becomes P diffusion. Now next is to make gate for PMOS. So we'll make it here. Okay, so this must be filled by poly. So I'll go to poly and press the center click. Okay, so fine, the DRC is 0. So now turn to make a NMOS. So for NMOS I already have P substrate, so over which I use N diffusion. So for N diffusion I'll make a structure first. So here my the width of my PMOS is 1, 2, 3, 4, 5, 6, 7. Okay, I'll extend it to 8, and then I'll try to keep the width of NMOS half of this. Okay, so 1, 2, 3, 4. Okay, so this must be N diffusion. So I will click this. Okay, so next step is to draw the gate poly. Okay, then I select the poly. So this is it. So now so since you know MOS is a 4-terminal device, so I have to take care of all the 4 terminals. Like if you see the example of PMOS, so the source is connected to VDD and the gate is connected to gate of NMOS, and from there we are providing input, and the drain, from the drain we are taking the output, and the body is connected to the VDD. Okay, so this is the one, and for this body should be connected to the ground. Okay, so we'll take care of all of this. So first we'll start with the gate one. So I'll extend the poly, and then I will connect this with VDD and this with ground, and then we'll take output from here because this side will become drain now. Okay, so I'll do it quickly. So it's metal 1, so this terminal will be ground. Okay, and for VDD I have to, so I have to connect this body also with the VDD. So I have to make this VDD inside the anvil only. So I have to extend the anvil for that purpose. So first let me draw the VDD rail, then I will extend the anvil. Okay, so metal 1, 0 DRC. Now I will extend this. Okay, so I will connect this source terminal. Okay, and here the source terminal of NMOS. Okay, so here is the question. Actually, these metal one layer is at another level and this diffusion is at another level, means the heights are different. So I will explain you what are these, and to connect these two I will use the contact. So I will explain these things step by step, why they are at a different level, what are these levels, and how to make the contact. So yeah, this is a structure. If you will see the 3D structure, so bottom one is substrate, over it there will be a SiO2, and over it they have shown one metal layer 1. So you can see it this way. If you see it, if you so side view is there, if you see it from the corner, and if you see it from the top it will look like this. And how about metal 2? Metal 2 is above the metal 1 but not connected. So it is clearly shown here in side view, this side view. Okay, so these are metal 1 and this is metal 2. Okay, and in between there is an insulator, and here also. So if you see the top view, it will look something like this: 2 M1 and over it M2, which are separated with SiO2. Okay, so here they have not shown the polysilicon, so I will show you the better picture. So here is the one. So P substrate, after that diffusion, and these poly, these, and then metal layer, metal 1 and metal 2. So if we need to connect metal 1 and metal 2, so we will use via contacts. So we will connect it like this. So because by default, if I have drawn one poly and I want to connect it with metal, so they both will not be connected until or unless I will not use these contacts. Okay, so this is via. So these via or contacts are the vertical connections. So till now we have seen the horizontal connection. Okay, so that's what I was trying to explain you here. So this one is the P diffusion. So P diffusion is here. Suppose this is P diffusion. Okay, and we have over it we run a metal 1 layer. So this is metal 1 layer. So there is a difference between P diffusion and metal 1. So we need to provide a contact to connect them. So for that we will use P diffusion contact. Okay, and the contact also has a dimension specification that it shouldn't be less than 4x4. But okay, let's try to make it wrong and we'll get the DRC, then we'll clean it. So I'm making it 3x3 initially. So what kind of contact? This should be diffusion contact, which will make a connection from diffusion till metal 1 layer vertically. So I need to search here. So generally contacts are like this cross. So I will search among the cross only. So this is poly contact, this is ND contact, and this is PD contact, the one which I was looking for, because I want to connect P diffusion till metal layer. So you can see white dots are there again and DRC becomes 2. So if you try to find the DRC, it will show you that you need one 4x4. So let's see, find DRC. Sorry, the command is DRC space find. So it is written here, diffusion contact width must be at least 4. Okay, so we'll press the U to undo this. Okay, now I'll make a proper one. 2, 3, 4. Okay, so I will use PD contact. So now this metal 1 is connected with this diffusion layer. So we have made this source connection. We have also made this gate connection, but for gate also I will use metal layer here. Okay. Alright, so metal 1, but at this point also metal 1 and poly are not connected. You can see it here, poly and metal 1 are not connected. So we have to establish one connection between these two, that will be called poly contact. So which will take poly till metal 1. It will be a vertical connection. So we can find here this easily. This is poly contact. Okay. So now these two are connected. Okay. So I'll go down to NMOS. So for NMOS, I'm supposed to connect its source with the ground. Here, source with the ground. So this is ground rail. So here I have to establish one connection from N diffusion till metal 1 vertically. So for that I'll use the contact, that will be N diffusion contact. Okay. ND contact. Okay. So like for both NMOS and PMOS, two terminals are properly connected. Now I'm going to connect the third terminal, which is drain. So both the drain are shorted and output is taken from there. So I'll short the drain here. So these remaining side of MOS will act as a drain. Okay. Okay. So the same story will here also. I have to make the connections. I have to make the contacts. I have to make the contact to connect this P diffusion with the metal one. So I will use PD contact. PD contact is here. Okay. And here ND contact. So I'll go to ND contact and will click the center one. ND contact. Okay, so it is done. So in this schematic, I have connected the three terminals of each MOS. Now I have to connect the body. This body should be ground. Okay, and this body should be connected to the VDD. So for that, we will use the contact, like in this structure of a PMOS. So this structure of a PMOS, drain and body should be connected together to VDD. Okay, I will connect the N well with this metal layer, the vertical contact I'll make, so that they both will get connected. So for that I will use this, yeah, N substrate contact. Okay, I'll use N substrate contact. So now body is also connected to VDD. So here it's good to make as many contact as possible. So I'll make one more. You can make 4 also, but I'll make 2 only. This side, for this, the body should be connected to the ground. So body is P substrate. So we are required to connect P substrate with the metal layer, which is at ground. Okay, so we will use this P substrate contact, P substrate P contact. Okay, so now all the 4 terminals are connected properly. So we are left with labeling only. So we'll provide in here, out here, VDD and ground. We'll make a point here first. So we'll convert this square into point, and then we'll use the command window. LAB level. This is ground, GND. or I can use the universal ground also by putting exclamatory mark. Okay, so you can see it has appeared here. So similarly I will, so the pointer is here now. I will make it as a VDD. So this is being assigned. So we are providing input to the common from the common gate. So this is the common gate. So from here we will provide the input. So I will write it here. So for input, I will select the edge. Label in. I am writing in only. So it has become in. And for output, the same way, output is taken from the common drain. So both drain are shorted here, and output is taken from there. You can see it, both the drains. So I'm assigning out to this. Okay, so labeling is also completed. So we have 0 DRC. So you can check all the connection, whether all the terminals are connected as per the schematic or not. So but this is, I already told you, this is not the optimum layout. We can reduce these distances as per the design rule. Okay, for the simplicity I made this a bigger layout. Okay, so if all the connection are proper, so I want to remove this schematic. Okay, so like I will save it now. File, save layout. So I'll give a name first. Extension will be .mag. Okay, I can save it from the command line also. Before actually extracting its netlist, I would like to tell you few functions here. Just suppose I want to copy this structure, so I'll click here. Okay, so first I have to select inside this box, so I'll press A. So everything is selected inside this box. So I'll go anywhere and press C. So that image will come, the duplicate C like this. So I can do undo for this. So this way I can do the copy, and that mirror, to make it mirror is also possible. So I'll press F. F is just mirroring this. You can see it here clearly. After selecting, press F. Okay, and how to unselect this, because I have already removed the square, but still it is selected. So press the shift A or something like that. Okay, by pressing A only it has gone. So this is one thing. You can copy it like this, and you can use the S also to see the running layer. Suppose this is the one, so I'll press S. Again I'll press S, so it is showing how this metal one is connected. Again I'll press S, so see, wherever the metal one is there, it is showing. Okay, fine. So these were few things, and you can move also. So if this is selected, press A. So this is selected now. I want to move it right, so I'll press the 6. It will go right. For back, I'll press the 4. So from your number pad, you can see it clearly. The arrow marks are also there. 8 will take it up. Okay, and then 2, 6, 2, So now this is its position, actual position. Oh, something has happened. This is not, it has gone. So I'll do the undo until unless it will reach to its original position. Not disturb its original position. Okay, now it has reached its original position. So now I can remove it. Okay, so fine. Now I'll extract the net list. The command is extract all. So first.ext file has been created. So I would like to see that file, first.ext ls. So there are so many files. First.mag, it's a layout file. First.ext, it's a spice file which recently it has generated. So I'll use vim editor vim space first.ext. Okay, so this is the one which is difficult to understand because the spice file that we are familiar with is not like this. So we will convert it exe file into spice file from here. So the command for this is ext to spice. So this .ext file will get converted into spice file. Yeah, it is finished. So now I would like to see this spice file. So ls, so spice file, yes, it is there, first.spice. So I'll see this spice. Okay, so here is the thing. You can see easily uh, the structure we have. Like we follow this convention generally: drain, gate, source, body. We write our code like this. So it has come out first, out in VDD. So it is fine. So out is the drain terminal only, and this is for PMOS. They have written PFET, and this is for NMOS. So I'll save it and I will run it. I'll do the transit analysis for this. So you can see some capacitors are also there. Some AD, PD, AS, PS are also there. You can explore these. These are the various parameters and the areas. Okay. So now we will see. We will simulate it in ngSpice. So I need to make it compatible for ngSpice so that I can run it and see the output waveform. So what I'll do, I'll try to see the transient analysis of the inverter, and for that first thing I have to include the models here. So how will I include it? What is the format? For this I usually follow this Stanford quick reference sheet. So here's the MOSFET model. So this is the format how to edit. Dot model, model name, NMOS or PMOS, level, and the other values. Okay, so I'm gonna write it here. So here the name is PFET. Yes. Level 49 and version 3.0. So the same thing I'll do with NMOS. Oh, sorry, it must be PMOS here because we are writing for P. So this time this model is for NMOS. Okay, fine. So here I'll decide the voltage sources. So first supply voltage V1, which is connected between VDD and ground, and the value is 1.8 volt. Next is the pulse, which is provided at the input. I call it V in, and which is connected between in and ground. And the syntax for writing pulse, and again search here. So here's the syntax: P naught G1, delay time, rise time, fall time, pulse within the period. Okay, so I'll write it fast. Then I want to perform the transient analysis. So for the tran, so these are the syntax for writing spice. So let's see whether it will work for us or not. Okay, so here we'll simulate the netlist ngSpice is file name, and here is the output. So this is the output blue one. So this is not that good, maybe because we have not drawn a good layout. So like if this layout was for learning purpose only, that was not symmetric also. Okay, so I'll try to open it and see it once. So this is our layout, you can see. So we can optimize it further to get the proper result. Okay, so you can see this layout now. So I did some few modification here. So now it's a symmetric on both the sides. This is source, this is drain. So both the side the dimensions are equal, and here as well. So now if I plot its output characteristic, then it should come proper. So we'll check if it's working fine or not. So see, now it is showing a proper result here. This red one is input and the blue one is output, and this is due to overshoot. And now I would also like to show you the netlist which we have simulated just now in the ngSpice. So I'll cancel this. I'll open the terminal. So I'll exit from the ngSpice. So what I did, I simulated this file, first layout.spice. So this one I have written for simulating this inverter. So what is there? So this is the same. So this one we got from the layout. This was like this layout spice file, and I have added few things which are required. This one I want to see is plot. So this is it. Now it's working fine for us. Yeah, you can see this is a layout and this is the output result, which is proper. So that's it in the layout. Thank you very much.